So I'm Mason. I'm going to be talking about a package that I developed with Karsten Bauer called OhMyThreads. So basically, just as a little bit of background, we can probably go over quite quickly. Julia has these threading primitives. The lowest level one we have is kind of spawn and fetch, at least at the user-facing level. And this lets you do all sorts of kind of crazy things like spawn exponentially many tasks, which can be very slow if you do it irresponsibly. Most of the time in scientific applications, people really don't want to be using like threads and spawn. They want to have some sort of loop that they're threading over and processing data in parallel instead of dealing with the details of these things. So they end up using this threads.@threads macro, which basically just you put it on a loop and it magically parallelizes it. It will break up your data into chunks and then applies basically the loop body as a function in parallel. Now, this is like a kind of for each like situation where it doesn't really have any primitive for combining the results of evaluation. So people get all sorts of bad ideas. I'm not sure I've seen this one done in practice because people usually find out right away that this is the wrong way to do it, but one's first intuition might be to just create some accumulator in a sum and then update it in a threaded loop and end up with nonsense. So that one gets caught pretty quickly, but it's like, yeah, basically my point is just that we don't provide a way to accumulate values very easily. So the suggestion that came about, like this is even in the blog post announcing our threading infrastructure, is to create some temporary stores equal to the number of threads, and then in your loop, ask for the current thread ID, and then mutate that temporary storage. This one's especially nasty because it usually gives you the right answer. And so, but if you have something a little more complicated than your simple example, say you have some special number type that for some reason yields to the scheduler in the middle of calculating the sum of two numbers, then you can get messed up results. Because basically what's happening here is that the task was spawned on one thread, and then it yields, and then it resumes on another thread. And so it mutates the wrong store, and all your results get screwed up. So a couple years ago, Karsten Bauer and I were having lunch, and we started complaining about @threads. And basically, the result of that was that we decided that it was easy to use wrong and not very flexible. So you're allowed to have one of those two, basically our concern was that there had been this package ThreadsX that was kind of the main thing that you could recommend people to use. Like, okay, this will mostly handle these things well, but ThreadX was getting more or less unmaintained. I was trying to keep up with it, but I was not doing a good job of keeping up with all the very complex infrastructure behind that package. We both had kind of slightly different visions of what we would ideally like to see multi-threading look like in Julia in the far future if all of our dreams came true. But we agreed that we could get at least 90% of what we wanted very quickly if we didn't try and be super ambitious with some big infrastructure plan and just made a little package that basically parallelized MapReduce instead of for each. So our hope was that maybe if we come up with some good ideas, eventually these can form the basis of some improvements to Base.Threads. Basically, there's two ideas in OhMyThreads. It's basically just we should parallelize MapReduce. This more or less comes from the transducers ideas. And we should take advantage of this great package, chunk splitters, and just use chunk splitters for users instead of asking users to figure out how they should be using chunk splitters themselves. So just because not everyone really knows what MapReduce is, it's one of these scary terms. Basically, for each is just saying, like Julia has these functions for each and MapReduce, and more or less what they do is like for each will take some function and an iterator, and it will apply your function f to each element of that iterator. MapReduce is basically like this, but with an accumulation step. So it has a combining operator op, and it has some initial value, and then you make your accumulator equal to the initial value, you loop over your vector, and at each step you're going to update your accumulator with this application of f of x. So you apply f of x to each element, but then you update the accumulator. This might seem complicated, but you're probably familiar with sum and prod. And both of these are MapReduces with the plus operator joining together items or the multiplication operator. So the thing is that if you have for each, it's actually kind of hard to implement MapReduce well, at least in parallel. But if you have MapReduce, it's trivially easy to implement for each. So this is kind of a better starting point, in my opinion. So you can write a for each loop just like this. You basically make some combining operator that does nothing, and then you MapReduce with an init of nothing, and you're done. So MapReduce is nice because there's very easy ways to tell people what is safe to parallelize with MapReduce and what's not. And basically, all that you need to know is that you have to not care about the order in which your mapping function f is being called. Your reducing operator needs to be associative. So this means that you can't care if you add b to c and then add that to a, or if you do a plus b plus c. And then depending on the details of your parallel scheduling, you might also require commutivity, because certain ways of parallelizing over data might reorder your data. But usually, like for instance, threads.threads, you own, or not threads.threads, but most schedulers only require associativity. So the basic interfaces we kind of developed for OhMyThreads is a MapReduce function, a reduce function, this is just without the f, a mapping function, because this is often something people also need. They just want, apply some function to every element of a vector and give me all the results. And then a mutating version of map, and also a tasks macro, because people like writing for loops. So if we go back to our yield example and do these nasty myints, do a t-reduce with plus over them, we end up getting the right answer. And the bad sum in this case was off by only 1. So you can see just how dangerous this is, because you can really test these things, and even if you have yielding, you can mostly get the right answer. So this tasks macro basically tries to act like @threads, except you can do things like tell it, okay, I have a reducing operator that should combine each result. So this sum could be written as @tasks for x and v, set the reducer equal to plus, and then return x. And that's equivalent to a MapReduce. We have this tmap function, just parallelized map, return vectors. And then just like @threads, we have some scheduling options. And the scheduling options right now mostly reflect what's in @threads, but it's extendable. You can just define a new scheduler and define what MapReduce means on that scheduler. So I would actually really like to implement a task group scheduler. I think that's something I've wanted for a while. So basically, our 4 different schedulers right now, we have a dynamic scheduler. This is the default. This is basically like regular @threads. We partition your data into chunks, and then each task gets a chunk of data. We have a static scheduler, which is like that, except we pin each thread. We make each task sticky, so it's not allowed to migrate. And this can sometimes improve performance in throughput-oriented situations, but you can't nest these. So if you have a threaded loop and you put another threaded loop inside of it, the inner one can't be, or I think neither of them should be static. We also have a greedy scheduler. This basically means that instead of partitioning each chunk goes to a task, we put all the data into a channel, and then tasks are pulling data out of the channel. This, however, means that your data can get joined in different ways, in different orders, and so you lose this requirement of only associativity. So if you use this greedy scheduler, you need a commutative operator. And then we also have a serial scheduler, which you can just pass this as an argument for the scheduler, and it will basically just do a regular MapReduce. And this is nice for cases where you want to use the same API for threaded and non-threaded functions. Now, where this starts to differ from @threads is that all these schedulers are customizable. You have fine-grained control over basically how many chunks how much you're going to chunk the data and how many tasks are going to get spawned as a result of that. So you can tell it, okay, I want 20 chunks, or if you have Julia started with like 90 threads and you don't actually want your data to be parallelized over all 90 threads, you could just say like, okay, only parallelize over 4 chunks, and then you'll only have 4 parallel tasks running at a time, and you won't swamp all your threads with all this overhead. Alternatively to n chunks, you can specify chunk size. So this is you saying like, okay, instead of, I don't know how many chunks I want, but I don't want any of my chunks to be, I want all of them to be a certain size. You can also specify minimum chunk size. This works with n chunks, and this is really useful for just saying like, okay, I want to parallelize this sum, but if you give me a teeny vector, please don't parallelize it. Just run it in serial, and then we can use the minimum chunk size to not spawn huge amounts of chunks. Then there's the split operator. So this basically tells it how the chunks are formed. So usually you kind of want your chunks to come, like you want the first item to be in the first chunk, the second item to be in the first chunk, and so on. But sometimes for load balancing reasons, for instance, if you're threading over a loop where, say, the first few elements you expect to take way longer than the last ones, then this sort of scheduling can be really bad for things like the dynamic scheduler. You might want the greedy scheduler, but that has more overhead. So just randomizing or like distributing each element to different chunks can give you better performance characteristics. And so with the round robin approach, basically the first element goes to the first chunk, the second element goes to the second chunk, the third element goes to the third chunk, and then we loop back. So the fourth element would go back to the first chunk and stuff like that. Round robin requires commutivity. And you can also specify, I don't want any chunking. So each point in the iterator goes to a new task or gets put into the greedy channel. Just a little note, sometimes one thing that makes it hard to work with high-performant multi-threaded code is that it's often type unstable because Julia's tasks are not parameterized on the function that they're calling or the return type of that function for somewhat good reasons. So if you fetch and spawn, just return the number 1, Julia's like, oh, I don't know what that could be. And so we basically somewhat sneakily use the return type function in the stable tasks package to recover this type stability, so that like tmap reduce over some vector, the compiler knows what that's going to return. We only do this as an optimization. We don't give users access to these inference results. We don't change behavior based on the inference results. This is basically just used to create type assertions that, okay, we have a upper bound on what the type of this, what the return type of each task is going to be before we sync them and combine all the results. And this just lets us take information from one place and move it forward. And this only works in particular because tasks run in a fixed world age. If tasks could execute their functions in an arbitrary world age, then this would be out the window, because then you don't know if the return types that you figured out before you ran it would be valid afterwards. A bit controversially, so Julia's threading primitives like spawn and threads and all this all work in terms of closures. So you can run into all sorts of funky issues. Like, for instance, say you thread over a loop, you label some variable A, you sleep for a bit, and then you put A into your vector, you can get weird results. Like, for instance, here, this should be 1 to 4. All of these are just 3. What happened was that you said A was equal to 1 outside of this loop, and this had a backwards propagating effect into this function body. And so this was actually a shared mutable container, and that was getting overridden in a raise condition, kind of like the first example with threads that I showed. So this is not really avoidable in Julia's design, but what OhMyThreads tries to do, hopefully this is legible, is we at least try and catch times where basically the closure being passed into any of our functions we try and detect if there's a boxed variable in there, and we're going to throw an error for you, and try and give you some hints and links to documentation on what happened. This is controversial. It has a lot of false positives. There are tons of cases where it was actually harmless, but I kind of think that this is good to do because if you're using threads, you probably care about performance, and these box variables are probably going to be very bad for your performance and stuff like that, and it just causes very confusing errors. So we basically say that you have to opt out of this error by using this allow box captures macro, and we also provide a macro localize, which you could put in front of this tasks. You could say localize A, and it would basically wrap this in a let block that would bring A local to that thing, and then it wouldn't be a captured variable. Probably, how much time do I have? Okay. So I think the last thing I want to mention about OhMyThreads is just that we try and provide some support for task local variables. So this is if you have some mutable storage that you might want to use in the course of your calculation. So in this case, we have some like vector of matrices, or some vector of matrices, and we want to multiply them together and then sum up the results and put these all into a resulting container. So like the serial way to do this is kind of obvious. You pre-allocate some matrix C, and then you mutate C with the mul function, and then sum them up together. There's many different ways, depending on your use case, that you might want to parallelize this. Kind of our preferred way with OhMyThreads that we try and make easy is we have this local macro. So you can basically say, okay, I have a local variable this is going to be stored in thread local storage, and it will just pull this out of the thread local storage. This is basically the initializer, and then it will multiply like this. And so this will get shared, but each task will have its own version of this C matrix, and so they won't interfere with each other, basically. And you can do this without the tasks macro, but it's not as nice, and it's actually also a little slower. But you can use this task local value structure that takes a function which initializes the task local value, and then you can access that task local value inside a multi-threaded function. Yeah, so that's all I really have to present today, but there's a lot more. In particular, Karsten Bauer did a really good job writing nice docs for OhMyThreads, and it just, even if you're not using the package, it has some very good advice on how to think about and use multi-threaded interfaces. So I'd recommend checking that out. I've got a QR code for it here if you want to.
Great. Let's give a round of applause to the speaker. And we have a full 10 minutes for questions.
Okay.
No. Oh, okay, there we go.
At the start, you had said this covers maybe 90% of what you would wanted. What's maybe like that extra 10% that isn't there yet?
So I think like what I want is I want the transducers library to be better. And I've been working on trying to fix up some of the transducer stuff, but it's a very big job, and I don't understand it very well. So what transducers lets us do is like we could do some of these map reduce operations and compose in various complications. Like say we could have maps that have filters in them and efficiently parallelize over a filtered operator. Stuff like that I think is somewhat hard to support in the current way we've designed OhMyThreads, but when you have all this extra infrastructure for transducers, you can do some fancier things. Yeah, that's kind of the main thing. The other thing is that I would really like composability of schedulers. So, so in the rewrite of transducers that I've been writing, like we have basically like, for instance, a distributed scheduler that can hold an inner scheduler. So you could say a distributed scheduler holding a threaded scheduler, holding a SIMD scheduler, and it would generate loops that partition the data, send each partition to different processes, and then on each process, it would multi-thread, and then on each multi-threaded sub-reduction, it would then use SIMD over that, and stuff like this. I mean, it's fancy. it's not that hard to do in some sense, but like we just wanted to get OhMyThreads out the door.
One more. Does there exist currently, and should there exist, a system that OhMyThreads can check whether it's already whether you're already in a threaded MapReduce and therefore not thread anything inside an inner MapReduce?
We don't have that. That would be kind of cool. I guess we could use a scoped value for that. I would kind of worry about the overhead. Yeah, I guess it wouldn't be much overhead to just set a scope value. Yeah, that's not a bad idea.
For users deciding between different threading packages, can you offer some high-level guidance on when to choose what, particularly if we're writing kind of HPC type things that might not at least explicitly yield and don't think we're yielding, but maybe don't know if something below us is?
Yeah, I think if you're relying on the idea that your function won't yield to be correct, then I think it's just a ticking time bomb. Like because whether or not something yields is kind of can be a result of optimizations. I don't really understand what processes can or can't yield, and I think these things are also allowed to change. Like I think dynamic dispatches, for instance, can yield, and
Allocations yield.
yeah, GC safe points yield. So
The compiler allows itself to put a yield anywhere it wants. Do not assume that you do not yield.
yeah, and so like everything could be fine. You could update Julia, and then like some escape analysis fails or something, and then suddenly you have a GC save point, and it'll just yield. And yeah, so I would really recommend not relying on that. I think OhMyThreads is kind of your best bet if you want a package to manage this for you. But you can also write you don't have to use a package for this. OhMyThreads is just trying to incorporate together some best practices that we've picked up. But I'm not an expert on this or anything, so I would suggest reading some of the docs and look, because like just spawning tasks, splitting up your work yourself, spawning tasks, and then putting the result in those, returning the result you want from those tasks is a really good way to do this.
But ThreadsX and polyester, is there some pro con?
So ThreadsX, I think, doesn't really offer anything that OhMyThreads doesn't offer. That was like kind of a design goal, was that this would be the next generation of ThreadsX. Okay, so that's folds.jl has a GPU backend. The GPU backend is broken, and that's just because I haven't had time to maintain it. But yeah, I mean, like there are nice things about ThreadsX, but it's really it's kind of bit rotting. Polyester really scares me. I mean, it is fast, but I don't know when it's just going to blow up in my face. So I try and stay away from it when I can.
So this, I mean, we have this in multiple domains and multiple applications, and it's at least not an easy problem to solve. And we have all these parallel solutions. Like, for example, OhMyThreads is kind of a mini Dagger in some ways. Can we try to achieve some vertical integration with this? Like say, we put these things in OhMyThreads, and then Dagger can maybe use some of those primitives to build on, so we don't have all these parallel things, and then users use several, and then they
I would really like this, but this is one of the things that can make projects like this go from a month to implement to multiple years to implement, and this is why Carson and I kind of didn't tackle that. But I have been talking to Julian about maybe Dagger integration, like a Dagger scheduler or something like this. I think this is something that he's particularly interested in.
Quick question then. I assume, but just want to clarify, reductions are also parallel, right?
Yeah. So, okay. So the final reducing step is so basically we spawn a bunch of in the default scheduler, we spawn a bunch of tasks. Each task does a MapReduce on their chunk of data, and then if you have n tasks, then we serially perform the last n reductions. So I think I did write up a scheduler that will do the pairwise reduction all the way down in parallel. I forget why it never ended up in the package. I actually couldn't really find cases that felt somewhat realistic where it worked. Even when I made like the reducing operator sleep for a long time and do weird things or do very heavy, complicated stuff like multiplying matrices, I found it very hard to find a good demo of where this was a good idea to do, and so I didn't. I think that was the main reason it didn't end up in the package, but
Okay.
but we should offer it.
I think so, because the HPC folks, especially when they're strong scaling things, the reductions can actually be a surprisingly large cost of if you're not doing them in parallel.
Yeah, I definitely agree, but this is mostly a distributed problem, and OhMyThreads is trying to stay focused on threads, but I think a satisfying solution to these things needs to incorporate distributed reductions as well. But yeah, we should have a pairwise reducing operator.
And one last question while next speaker sets up. Yes, it is. If not, let's thank the speaker again.